So this is section 2.6. We're going to talk about rational functions and their graphs. Remember, when we refer to rational functions, we're referring to fractions. And simply, when we talk about rational functions, we're talking about quotients of polynomial functions. So we're going to have a polynomial function in the numerator, a polynomial function in the denominator, and remember that the denominator cannot be 0, right? Otherwise it's undefined. Let's recap on our domain. We talked about the domain in chapter 1, I believe. Remember, the domain is all real numbers except if we have a variable in the denominator, then we're going to set it not equal to 0. Because remember, anything equals 0 in the denominator, it's undefined. So if I have 1 over x minus 6, if x is 6, then it is undefined. And if we have 1 over x minus 6, if x is 6, then our denominator is undefined, right? Remember?
Yeah.
Okay, if we have a square root and a variable in the square root, we set it greater than or equal to 0 because we can't have imaginary numbers in our domain. If that square root is in the denominator like this, that's when we set it greater than 0, right? Because now we're excluding anything that makes the denominator 0 and anything that makes the square root imaginary. Look at our first example. It says find the domain of the rational function. So what should I do? Good, so I'm going to take x minus 4, set it not equal to 0. So what value am I not allowed to have? 4. So for all values of x, x cannot equal 4. This would be our set builder notation. Or we can use interval notation, negative infinity to 4, union 4 to positive infinity. Okay? What this does, remember, let's take a look at our numerator. The numerator, I can factor that to what two factors?
X minus 4 x plus 4.
Good. Okay, and what happens here? Okay, x minus 4 reduces, and I end up with x plus 4. Let's say I asked you what's the domain of what we have left. What would you say?
Negative 4.
Okay, don't make the mistake and say all real numbers, because remember, this to this, they go together. So the domain is really what's happening here. It's just this is reduced. That's all it is. So it's the same thing, except it's simplified. So if I were graphing it, yes, I'm graphing a line, but I'm excluding the value of 4 because remember, we started off with this denominator. Even though it reduced, this is still the given. This is still what I'm interested in. So if I were graphing this, let me just create a quick graph so we can get an idea of this. Let's go by 2, 4, 6, 8. 2, 4, 6, 8. And I'm going to graph the y-intercept at 4. And then I'm going to go up 1 over 1, up 1 over 1. And when x is 4, y is 8, but that's excluded from the domain, so that's going to be an open circle. Remember that concept that we talked about before? So this is all describing one rational function, and that's this one. This is its graph, and this is the function simplified. So the domain, you can see both on the graph and on my notation here that the only thing I'm excluding is 4. Alright, so let's take a look at another example. So here we want to find the domain of the rational function. What could I do here? Okay, so set the denominator not equal to 0. I have a couple options here. I could either start solving for x or I could factor. Your choice. But I'm just going to bring 36 over, take the square root of both sides, and we end up with what? Good. So x cannot equal plus minus 6. So if I put positive or negative 6 here, then it would be undefined. So for all values x, x cannot equal plus minus 6. If I'm using interval notation, I'm excluding negative 6 and 6 from the domain. Okay, so here we have vertical asymptotes of rational functions. And I want to talk about what the definition of this means. So we have a vertical asymptote at what is going to make the denominator undefined? What makes the denominator undefined here? 0. So if x is 0, I have a vertical asymptote. And if you look over here, as we approach 0 from the right, we start shooting out towards negative infinity. So we're approaching negative infinity without bounds. As we approach 0 from the left, then you could see your graph increasing towards positive infinity. So we're approaching positive infinity without bound. That's the definition of what an asymptote is. Okay? Let's take a look over here. We have arrow notation approaching from the left or right. That's what I was using a moment ago. If we approach, x approaches a from the right, that's what this notation means. Arrow means approaching. This plus sign means from the right. This minus sign means from the left. If I see positive infinity, we're talking about it increasing, x increasing without bound. And x approaching negative infinity, that is, x decreases without bound. Okay, so if you see me using this notation or saying approaching from the left or right, increasing or decreasing without bounds, this is the notation you use. So let's take a look at another graph that could be a rational function. We have 1 over x squared. The only difference is what happens when I input negative values into x, guys. They stay positive. Good. And so I should see that behavior in my graph, and I do. Okay, so nothing is outputted over here in the negative parts of our coordinate plane, right? So as x approaches 0 from the right, f of x approaches positive infinity, and that's the definition of an asymptote, right? So I can clearly see that I have an asymptote here. And as x approaches 0 from the left, f of x, or your function, or your outputs, are approaching positive infinity. So that's all this is saying as well. Okay, so let's take a look over here at our vertical and horizontal asymptote. We have a vertical asymptote when we are approaching positive or negative infinity without bound, when I approach from both ends towards that point. Okay, and I have a horizontal asymptote when f of x is approaching b as x approaches positive or negative infinity, and I'm about to show you a couple of examples to that. So let's take a look at a couple examples of our vertical asymptotes. Let's take a look at this one first. Here's our given. What's going to make this denominator undefined? Plus minus 3. Do you agree? Okay. So at plus minus 3, because nothing reduces here, right? Do you see nothing reduces from the numerator to denominator? Because that's true, I should have vertical asymptotes at plus minus 3. And I do. If anything were to reduce, that's when you have that open circle and not a vertical asymptote. So here I can clearly see my vertical asymptotes happening at plus minus 3. Let's take a look at this next one. Okay, the denominator again is undefined at plus minus 3. Do you guys agree? But this time the binomial of x plus 3 is going to reduce. So if I were to rewrite this, x plus 3 over x plus 3x minus 3, here I could see that x plus 3 reduces. So that means we're left with 1 over x minus 3. Now let me ask you, am I still allowed to have negative 3 as part of my domain? No, because the original excludes it, right? But the only asymptote that's occurring, the vertical asymptote, is this one at positive 3. And I should see that in the graph. And that's exactly what we have right here. So at positive 3, we have a vertical asymptote. And at negative 3, we have an open circle. Here I have the definition of what an asymptote is. As I approach 3 from the left and from the right, our function is increasing and decreasing without bound. Do you guys see that? Okay. At negative 3, that doesn't happen. We just approach it from the left and from the right. I have an open circle. Let's take a look at our third example. Is anything going to make that denominator undefined for h of x? No, because of this plus 9. It doesn't matter what value that I put in here. I'm always adding 9. Nothing would ever be undefined here. Therefore, I shouldn't have any vertical asymptote in the given, and I don't. Alright, so let's take a look at this third example. It says find the vertical asymptote if any of the graph of the rational function. So what I want to do is factor if possible first, then reduce, and then identify my vertical asymptote. So this, we can reduce the denominator to x plus 6, x minus 6, because we took a look at this before, remember? Does anything reduce from there? No. Okay, that means that both of these are vertical asymptotes. So after I set them equal to 0, x equals negative 6, and x equals positive 6. So our vertical asymptotes are x equals negative 6, x equals positive 6. Let's take a look at our definition for a horizontal asymptote. Before I start talking about this, I actually want to show you over here what I mean. Okay, actually let me show you over here. Let me zoom in. Okay. Alright, so horizontal asymptotes, what we're going to have is, if I have a polynomial, let's say f of x equals 2x squared plus x plus 1 over 3x to the fourth plus x cubed plus 2. I just made that up. Okay, what is the degree of the top polynomial? The degree is 2. Remember, the degree of the polynomial, we look at the highest exponent. What's the degree of the denominator? 4. Do you agree that the degree of the top is less than the degree of the bottom here? Okay. So when the degree of the top is less than the degree of the bottom, your horizontal asymptote, I'm going to abbreviate it, HA, is always y equals 0. Alright, now I'm going to make up another example. Let's say I have f of x equals 4x cubed plus 2x squared plus 1 over 2x cubed minus 5. Okay, what's the degree of the top? 3. What's the degree of the bottom? 3. If they are the same, at this point I'm just going to start abbreviating it. So if the degree of the top is equal to the degree of the bottom, what we do is we take the leading coefficient of the top over the leading coefficient of the bottom. So y equals leading coefficient of top over leading coefficient of the bottom. So what's the leading coefficient of the top for that example? 4 over 2, which reduces to 2. So the horizontal asymptote for that made up example is y equals 2. Okay. Okay, so I'm going to make up another example. Let's say we have g of x equals 5x to the 5th over 2x cubed plus 3. Okay. Do you agree that what's the degree of the top?
5.
And the bottom?
3.
So if the degree of the top is greater than the degree of the bottom, there are no horizontal asymptotes. And I just want to point out that the examples I just showed you guys is what this is saying. So I have the degree of the top is n, the degree of the bottom is m. So if the degree of the numerator is n, the degree of the denominator is n. If n is less than m, your horizontal asymptote is y equals 0. If they are the same, you take the leading coefficient of the top over the bottom. If n is greater than m, you have no horizontal asymptote. So let's just explore these graphs here. Let's take a look at the given. The degree of the top in relation to the degree of the bottom is smaller. Good. Therefore, what's your horizontal asymptote?
0.
Good. And you see that happening here, y equals 0. Alright, let's take a look at this next one. The degree of the top in relation to the degree of the bottom is equal. So your horizontal asymptote is 2. 4 over 2. And then this is what you have. Y equals 2. And then our last one, the degree of the top in relation to the bottom is greater, so you don't have a horizontal asymptote. Now let's actually find the horizontal asymptote given a rational function. Always determine the degree of the top in relation to the bottom first. What is it? Okay, the top is less than the bottom, good, so n less than m. That means that your horizontal asymptote is what, guys? Good, it's y equals 0. Make sure you write it as an equation that you can graph. Okay, so don't just write 0, it's y equals 0. Alright, so the degree of the top in relation to the degree of the bottom in finding the horizontal asymptote, what is it, guys? It's equal. Okay, so n equals m. Remember, you take the leading coefficient of the top, which is? And the bottom? So your horizontal asymptote is occurring at y equals 6.